The 500-step transistor. A single transistor on a 2-nanometer chip now requires more than 500 individual process steps to manufacture. For decades, the industry focused on the lithography machines that draw the blueprints for these circuits. But we have reached a point where the blueprint is no longer the problem. The bottleneck has shifted to the physical materials required to build those microscopic structures, without them collapsing or leaking electricity. This week, Applied Materials reported that its gross margins hit 50% for the first time in 25 years, because the world's leading chip makers are now paying a complexity tax. They are no longer just buying machines that print patterns. They are buying machines that can manipulate matter at the scale of a single atom. This shift in the spending mix is the reason for the surge in demand for gate-all-around transistor tools beyond the lithography wall. While everyone watches the delivery of high numerical aperture lithography systems, the real battle for 2-nanometer supremacy is happening inside the vacuum chambers where films are grown. At these scales, traditional silicon oxide isolation layers begin to erode during the manufacturing process, causing parasitic capacitance that drains battery life and generates heat. Applied Materials recently introduced a precision selective nitride system that deposits protective layers with atomic scale tolerances. Think of it like building a skyscraper where the steel beams are only a few atoms thick. If the insulation is off by the width of a single molecule, the entire processor fails. This is no longer a design challenge. It is a chemistry challenge that gives materials engineers more leverage over the roadmap than the architects themselves. This material precision is exactly what is enabling the shift to nanosheet architectures. The gate-all-around inflection, the transition from FinFET to gate-all-around transistors, is the most significant architectural change in 20 years, and it is a massive revenue multiplier for equipment providers. In the old design, the gate controlled the channel on 3 sides. But at 2 nanometers, that is not enough to stop electrons from jumping the fence. The new architecture wraps the gate entirely around the channel. Building this requires the Trillium atomic layer deposition system, which integrates multiple metal deposition steps into a single vacuum run. By doing this in one platform, chipmakers can tune the threshold voltage of billions of transistors simultaneously. This level of integration is the only way to manufacture the 300 billion transistors found in the latest artificial intelligence chips. But even with a perfect gate, there is still the problem of how to actually power the device, the backside power revolution. Engineers are now flipping the entire chip upside down to solve the power bottleneck. Traditionally, both data and power wires were crammed onto the front of the silicon, creating a crowded mess that led to voltage drops. Backside power delivery moves the power lines to the rear of the wafer, but this requires thinning the silicon down to a fraction of its original thickness, and then etching through it with perfect alignment. Applied Materials is seeing record revenue from this shift because it requires a completely new set of tools for epitaxy and chemical mechanical planarization. It is a dual upgrade cycle. Chipmakers are spending on gate-all-around for performance and backside power for efficiency at the exact same time. This explains why management just raised their 2026 growth forecast by 50% in a single quarter. This convergence is turning the fab equipment market into a winner-take-all landscape. The Real Implication. The shift from lithography-led scaling to materials-driven performance marks the end of the era where chip design was the primary source of competitive advantage. We can clearly see from the recent surge in gate-all-around tool orders and the high-density packaging revenue growth that the physical limits of matter are now the ultimate gatekeepers of the artificial intelligence boom. For investors and strategists, this means the value in the semiconductor supply chain is concentrating in the hands of the few companies that control the atomic deposition and etch steps. The record 50% gross margins at Applied Materials are not a peak. They are a reflection of a new industry reality where the complexity tax is permanent. Because each new node now requires significantly more materials intensity than the last, the capital expenditure floor for foundries has moved permanently higher. Watch for the first high-volume 2-nanometer production yields this summer as the definitive signal that this materials moat is unshakable. Subscribe for more.